Guys, let's take a look at today's lesson. What we're going to be looking at are basically some vocabulary words, some concepts that have to do with vectors is what we're going to look at today. We'll spend a couple of days on vectors. Today we're going to be looking at vectors from a geometric perspective, like how does it look if we draw one, what does it mean, kind of visually, what is a vector. Tomorrow we'll get into the algebraic representation of a vector, but today we're going to focus on the geometric representation. Let's get some vocabulary words out of the way. What is a vector? Well, a vector is an object that represents two different quantities. Size or magnitude and direction, both of them. Some examples of what we might use a vector to describe would be, velocity, acceleration, force, displacement. All those are things that we can use vectors to describe. So we're looking at magnitude or size and direction. An equivalent vector, that's pretty much like common sense, right? What would an equivalent vector be? What would it take for vectors to be equivalent? Well, they would have to have the same magnitude, and they would have to be going the same direction. That kind of makes sense, right? If they're going to be equal, they need to have both of these components equal, the magnitude and the direction. A unit vector is a vector whose magnitude is 1 or length is 1. If you think back to the unit circle, why do we call it the unit circle? Because the radius is 1, right? A unit means 1. So a unit vector has a length or magnitude of 1. So sketching, we're going to sketch vectors today. We need to talk about the parts of the vector. So the beginning of the vector, the initial point, is called the tail or the foot. Okay, that's the beginning of the vector. The end of the vector, the terminal point, is called the head, and it has an arrow. Okay, and it might look like a ray to you, like for example from geometry, remember those rays? It's not a ray because this has a specific length. A ray just kind of pointed in the direction and kept going forever, right? I mean, it was just like half of a line. This is not half of a line. This actually has a beginning and ending, and it ends right here. I mean, that's the beginning of the vector, that's the end of the vector. It doesn't keep going. The reason it has an arrow on it the reason is not that you continue moving that way. The reason is to indicate which way you're moving. That's why it has an arrow on it. It's just telling you which way is the vector going. Alright, and the length of the vector is called the magnitude. I do want to talk about this symbol right here. So the double bars means magnitude. Many textbooks will write magnitude with single bars. Okay, and that's okay, but I'm going to explain why I think it's important for us to understand double bars. So in multivariable calculus, in calculus 3, we use double bars and single bars all the time. This has a completely different meaning for us in calculus 3. This means something completely different than this. This does not mean magnitude. This means determinant. In calculus, this means a determinant. So I don't really want to use the single bars to represent magnitude. I want to use the double bars. Will you see things with the same? And plus, I think also this gets confused with absolute value. It looks like absolute value, doesn't it? That's not what it's meaning when it's regarding a vector. It's really talking about magnitude. So I'm not going to use the single bar. I'm going to use the double bars. So this is magnitude or length of the vector. Okay, so I'm just explaining the notation. Could you see this? Yes, but I'm going to avoid it when we're talking about it. I don't, for both reasons. I don't want us to think that it's absolute value, and I don't want us to get confused with, determinant. So operations on vectors. We can add vectors together. We can do, subtract vectors. We're going to do that graphically today. We're not going to do that algebraically. We'll do the algebraic forms tomorrow. So what does it look like to add vector AB and BC? Okay, so if this is vector AB, see it has a definite beginning and a definite ending. This is vector BC. In order to add them together, I have to place them head to tail. I cannot place them tail to tail or head to head. It does not work that way. Okay, so that's really important for us to visualize what's happening with this. When I'm adding these vectors together, and it doesn't technically matter which one I put first, but I really think we should put the first one first, right? We would draw AB. So here's our AB, and then we would attach BC to it. So see, BC is attached to it, and that will result in, it's called the resultant vector, in vector AC. The resultant vector is typically drawn with a dotted line. That's usually how we would draw that. So we have the two vectors are being added, and there's our resultant vector. What does a resultant vector mean? What is that? It basically means that this vector AC has the same effect as the other two put together. It's the result of those two, whatever it is, forces. That's the result of what happens. That's its resultant. So what we're going to be focusing on today is drawing vectors. We're going to draw them, and we're going to find the resultant vector geometrically today. And we'll work on algebraically tomorrow. So we are able to subtract vectors. If we have vector v and we write it as negative v, basically what that means is that these two vectors, this one and this one, will have the same length or magnitude, but they'll be in exactly opposite directions, like 180 degrees opposite, exactly opposite directions. We can move a vector around. Okay, it doesn't have to be at the origin, or we can move it around, but it would be like translations in geometry, right? We can slide it all around, but we can't rotate it or shrink it or do anything else to it. But we can move. It does not have to be at the origin. We can move it anywhere. And the last concept, general concept we're going to talk about today is a zero vector. It basically represents no displacement. I mean, we don't use the zero vector that often, but it's a thing, so I wanted you to know it's a thing. Usually is a bolded 0 if we're going to be using the zero vector. Let's see what else we have. Okay. The only other thing, oh, here we go. This is what I was looking for, right here. We are allowed to multiply by a scalar. That's a vocabulary word, scalar. It just means a constant, like 2. You know, a scalar would be 2. So you can multiply a vector by a scalar, and we're going to get into those kinds of computations tomorrow. But I do want to talk about component form just briefly, because your daily work starts out with you drawing a vector in component form. So this is called a chevron. Okay, these things right here are called chevrons. That's how this has got component form. This is a component form of a vector. And we'll look at this in more detail tomorrow, but I just need you to understand what it means just so that you can draw a vector. Okay, if I'm looking at -2, 3, now that's a vector. It's in component form. This is my horizontal component. And this is my vertical component. Kind of like a point. It's not a point, it's a vector, but it's kind of like a point. So if I'm going to be drawing this vector, I would go left 2 and up 3, and that's where I would put the head of the vector, and it would look like that. Okay, that would be this vector drawn at the origin. Do I have to draw it at the origin? Absolutely not. I can draw it wherever I want to. I could draw it, you know, anywhere. What if I wanted to, I don't know, let's say I want to put the tail here. Then I would just need to go over 2 and up 3. And so, you know, my vector would look like that. It doesn't matter where you draw it. It just has to be horizontal movement 2 to the left, vertical movement 3 up. That's where you put the end of it. Okay? So this is just to get us to be able to draw a vector so that we can draw all the other stuff with it. That's all. We'll go way more into detail on this tomorrow. All right, questions for me before we start? We have a couple of examples to work. Do we have any questions yet? Okay, so let's go to our examples. We're covering 2 main topics today. One is drawing the vectors. Okay, so that's our first example where we're going to draw them. And the second one is finding the resultant. Okay, so let's work on the drawing a vector first. So here the vector's drawn for you, unlike on the daily work where I give you the component form and you have to draw it. So it's already drawn for you, and they're asking us to do 2u plus v. They're asking us to draw that, you know, vector addition. So what I'm going to do is I'm going to start with the 2u. What do you think the 2 means? What am I supposed to do? I'm supposed to double the length. This is what I'm supposed to do, right? The 2 means double the length. So if I'm looking at vector u, if I create vector u by going left 2 and up 3, I'm going to need to double that, aren't I? Do I have to start the vector right here where that one is started? No, I can put it anywhere I want. Okay, I'm going to do that just so that we're clear. But I can draw it anywhere I want. So I'm going to go, so I would go over 2 and up 3. That would be one rendition of the vector. Now I need to do that again, right, because I'm doubling it. So I go over 2 and up 3. And that would put me, because we went left, up. So left 2, or you could go left 4. 1, 2, 3, 4. Up 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here it is. No, I can't count. There we go. Okay, there is our 2, and let's label it 2u. Okay, so here's my initial point, and there's my terminal point. Initial point is the beginning of the vector, terminal point is the end of the vector. Now, in order to add vectors, I must put them head to tail. Like, it's not a choice. I have to put them head to, I can't just now that I have this one placed, I can't put v anywhere I want. It has to start when 2u ends. So I have to put the tail of vector v here. Now vector v goes 1, 2, 3, 4, 5 up and 2 over. So 1, 2, 3, 4, 5 and 2 over. So there's my vector v. And I'm labeling it vector v. Now we're going to draw the resultant. So we're going to use a dotted line to draw it, because that's just the norm, is to use a dotted line. So the resultant is basically connecting the beginning of our vector, our string of vectors, to the end of the string of the vectors. That's all. So we draw our resultant. And this resultant's name would be 2u plus v, because that resultant vector has the same effect as the combination of the other two. Okay, are we okay so far? So we're building, hoping that we're building some kind of a visual understanding of what vectors are and how they work. Okay? Questions? All right, let's move to the word problem. So here we're asked to make a scale drawing showing a force of 20 newtons pulling an object east and another force of 10 newtons pulling the object in the compass direction 150 degrees. So you're probably going to be shocked. I'm not a big physics person. I like physics, but I'm a mathematician, right? So I don't deal with physics a whole lot. But when I first started looking at vectors and like force, I'm like, what? 10, 20 newtons? That means that's the length of the vector, which seems weird. The force is the length of the vector. Okay, that's the magnitude. So if I'm drawing it geometrically, I would draw it like 20 units long. I mean, that's what I would do. If it's 20 newtons, it'd be like 20 units long. And we're going to, let's see, that one is east. So that means exactly due east. So I would draw my vector. So let's say that that's my vector that's 20 newtons long. Okay? So now they want us to draw one that's 10 newtons long, but in a compass direction of 150 degrees. I don't have a choice of where I put this one now. I'm going to be adding these vectors together. All right, this vector has to start when the first vector ends. So what I would suggest that you do is, like long ago, many moons ago, you know, put a north line there. You don't have to put an arrow, just a dotted line, north line, because we're going to have to measure. Right, we need to measure this 150 degrees. And we're back to, I know, measuring off the vertical. It's very troubling, but that's where we are, back to the vertical. So we move above, right? Remember, we're going to rotate, you know, the wrong way, which is clockwise. Okay, sorry. We're going to rotate clockwise 150 degrees. So if I rotated 90 degrees, that would put me right here, right? So it's going to be more than that. All the way around would be 180. So I need to go 150. So let's just say here. And this vector has to be, now, I mean, we need to try to draw it kind of to scale. Like this may start reminding you of something that we've done in the past. So if this is 10, let's see, you know, we really would want this one to be twice as long. And that's close. I mean, I have it close. It doesn't have to be perfect, but it needs to be kind of close. This angle measure right here is 150 degrees. Okay, so are we okay with the drawing so far? We have our two vectors drawn. They're being added. That's what we do, head to tail. And then I'm going to draw the resultant vector. So this is a dotted line that connects the beginning of this string of vectors to the end. Okay, so now what they're asking us to do is to draw the resultant. We just did. That's the resultant force vector. And then find the magnitude and direction of the resultant force. I need the length of that. Now we're going to think geometrically with the information that we already know. We'll get into component form tomorrow. But let's see, how in the world do you think we could find that? Oh, it's a flash from the past. Oh, yay, yes, law of cosines. Oh, you thought we left that behind? No, not really, never. We don't get to leave anything behind. That's the beauty of this. So I need to use law of cosines to find that. Tomorrow I'll show you a different way when we're working algebraically with vectors. But today we're going to work with it geometrically. It'll work. We're going to do it this way. So I need this angle right here. So let's kind of look at what we have and try to figure out what that angle is. You know, if this is 150 degrees, then this little angle, we would know what that little angle would be, right? It would be 30 degrees, so that's going to be 30 degrees. And if this is due east, which it is, and this is a north line, then that would make 90 degrees, right? So that would make 90 degrees. And so we can use that information to find this whole angle, right? That's what we're going to do. And so, yes, this is a calculator lesson. Part of it's calc. If you have your calc, go ahead and get it out. And so we'll work on finding the magnitude. So we would say x squared equals 20 squared plus 10 squared minus 2 times 20 times 10 cosine of, let's see, that whole angle is 90 plus 30, right? 90 plus 30, so 120 degrees. Yay. Now, since cosine of 120 degrees is a negative 1/2, we're not going to have a weird decimal here. This is unusual. Just let me let you know, this is unusual. Normally we would have a weird decimal. You're used to that, right? With all the other applications we've been doing with law of cosines, you know, in the past. So, but with this one, since cosine of 120 is a negative 1/2, we actually get that x squared is 700, and we're able to do an exact value here. So x is going to be 10 root 7. Okay, so what does that tell us? That gives us the magnitude of our resultant vector. So our resultant vector is 10, has newtons of 10 root 7. The resultant vector's magnitude, the magnitude of the resultant vector is 10 root 7 newtons. Okay, are we okay with finding that length? Same thing as the magnitude for a vector? Okay, so now let's look for direction. We need direction. All right, so we can kind of see these vectors are going, you know, east and then down here. So this vector, this resultant vector is going to be headed this way, right? I mean, that kind of makes sense, right? If we're going, so my choice is the vector, this resultant vector is either going this way or that way, down or up. That's the only choice I have. It's just two directions, right? I would either put my arrow here or there. Since these vectors that created it are headed this way, I hope that we see that this vector would be headed that way, right? Not this way. Okay. So what I need to do is I need to find this angle measure. That's the angle measure I'm looking for. I'm measuring it from the tail, right? Measure it from the tail, not from the head. So this would be the head, right? It's headed that way. I'm measuring from the tail, so we need that direction. All right, so let's kind of think about this. If this is the north line and this is east, I think we can see what this angle would be pretty quickly, right? That's going to be 90 degrees. So this is 90 degrees right here. What else would we need? Wouldn't we need this angle measure right here? I'm going to call it alpha. I mean, you can call it whatever you want. I'm going to call it alpha. How can we find that angle measure? Law of sines, yay, right? It's just all this lovely review. All right, so we have sine of 120 degrees over 10 root 7 equals sine of alpha over 10, right? And so again, if this were not exact, we would need to use that whole decimal when we're calculating, right? We don't round to the very end, otherwise our answer is going to be off. So we keep that whole number in when we're doing our law of sines to calculate. Okay, so we would, y'all are quite familiar with this. We would cross multiply, work through that. Once you do, your alpha should be 19.1066 degrees. Now, is this 19.1066, is that our direction of our resultant vector? No, right? It just helps us get to it. What do we need to do to this? We add the 90 to it, right? So we would say the 19.1066 plus 90, and that's going to give me my direction of 109.107 degrees. So this is the information that they asked for, the magnitude and the direction, and we calculated that using prior techniques. Now we're going to learn some actual different kind of techniques tomorrow to do the same thing, but I want you to see this way because I think this is comfortable. We've done this before. It makes sense. Any questions about that? Okay.